In this video, we're going to focus on total derivatives. This is actually a continuation of the discussion on partial derivatives. Okay, so first let's talk about total differentials. Remember, differentials, these are the individual components of the derivative symbol, right? So for instance, if you have y equals f of x, then its derivative is dy dx, right? And the differentials in this case is dy, the differential of y, which is a separate expression compared to dx, the differential of x, right? So these are differentials, dy and dx. This is derivative, dy over dx, all right? So for functions that are defined in terms of two or more independent variable, say for instance z as a function of x and y, then we have partial derivatives, right? If you can still recall, we have partial derivative of z with respect to x and partial derivative of z with respect to y. So for this one, it's total differential, so that's dz, okay, the total differential of z is equivalent to the partial derivative of z with respect to x times the differential of x, all right? So notice the difference between the differentials and the derivative and the partial derivative. Okay, so we have here again partial derivative of z with respect to x times the differential of x dx plus partial derivative of z with respect to y times the differential of y dy. Okay, so this is again the total differential of the function z, where z is uh, defined in terms of x and y. Okay, now if we have a function in terms of, or defined in terms of three variables, say this one, u, which is defined in terms of x, y, and z, then we can have three partial derivatives, right? Partial derivative of u with respect to x, partial derivative of u with respect to y, and partial derivative of u with respect to z. And then its total differential, which is du, is defined as the partial derivative of u with respect to x times the differential of x, okay, plus partial derivative of u with respect to y times differential of y plus partial derivative of u with respect to z times the differential of z. Okay, so these are just uh, formulas that we can use if we are asked to find total differentials. Okay, for instance, if we have z equals 3x cubed times y plus 5xy squared, let's say we are asked to find the total differential of z, then we can use this working equation. So first we need the partial derivative of z with respect to x. Okay, so hold y as constant. We have here 9x squared y plus 5y squared. And then partial derivative of z with respect to y. So hold x as constant. We get 3x cubed plus 10xy. All right, and then plug in these equivalent expressions to the formula of the total differential of z. Okay, again, the total differential of z is this one from the formula, and then plug in the equivalent expressions for the partial derivatives. All right, so partial derivative of z with respect to x, it's this one, right? Copy. Okay, and then just copy dx also from the formula. And then partial derivative of z with respect to y, this one, copy. Then again, copy dy from the formula. This is now our total differential of z. All right. since we now have an idea what's a total differential, let's move on to total derivatives. Okay, again, differentials, examples are dy and dx, all right? And then derivative is the ratio between dy and dx. Differentials and then derivative, okay? So let's talk about total derivatives, all right? Again, let's say we have z as a function of x and y, where in this case we have parametric equations. We can express x and y as functions of some other variable, a third variable, or a parameter, if you will. Okay, in this case t, all right? And then remember that we have the total differential of z from the formula that we discussed earlier. To get the total derivative, in this case with respect to t, because the overall independent variable in this case is t, then we can have the total derivative of z with respect to t. That's dz dt. This is now a total derivative as opposed to total differential, which is only dz. Okay? So this time, we need to find out what's dz dt. So to get dz dt, we just divide both sides of the equation by a dt. Okay? And it will result to this equation. All right? This is now the total derivative of z with respect to a parameter, in this case t. Okay? If t is time, then we have here time rates. All right? And then, for instance, if we have a function in terms of, or defined in terms of three variables, x, y, and z, okay? Again, where x, y, and z are functions of a third variable or a parameter. And then recall that this is the total differential of u if it is in terms of x, y, and z. So to get, in this case, the total derivative of u with respect to t, then we just have to divide both sides of the equation by the differential of t, or dt. Okay? So it will result to this equation. Now let's try some examples so we can have a better understanding of this concept. Okay, first, we have here z equals xy, where x is sine theta and y is cosine theta. Find the total derivative of z with respect to theta and in terms of theta. All right. So again, this is the given. In this case, the parameter is theta instead of t. Okay, so we'll be replacing t with theta in the formula. All right, total derivative of z, again, instead of t, this is with respect to theta. Okay, and this is just from the formula that I mentioned earlier, right? This is our working equation. So from here, we need the partial derivative of z with respect to x. We need dx d theta. Okay, partial derivative of z with respect to y, and lastly, the derivative of y with respect to theta. So let's start with the first one, partial derivative of z with respect to x. So let's look at this equation, all right? Uh, take the partial derivative of z with respect to x. So we should hold y as constant, all right? Therefore, partial derivative of z with respect to x is y, okay? And then next, let's try the partial derivative of z with respect to y. Again, looking at this equation, z equals xy, this time holding x as constant. So, partial derivative of z with respect to y in this case is x. Alright? And then for dx, d theta, so let's look at this equation. Take the derivative of x with respect to theta. So, sine theta, derivative with respect to theta is cosine theta. Okay? And then lastly, for dy d theta, let's look at this equation. Find the derivative of y with respect to theta. So cosine theta with respect to theta, that's negative sine theta. Okay? And then all we need to do is to plug in these equivalent expressions to the working equation. Okay? So plug in and then simplify, we get y cosine theta minus x sine theta. And then going back to the problem, we are asked to find two things, or we are required to do two things. Take the total derivative of z with respect to theta. We already did this part. And then we have to express it in terms of theta only. Okay, so this means we should only see the variable theta in the right side of the equation. Okay, so this means that we have to eliminate y or convert y and x to their equivalent expressions in terms of theta. Okay, and we know y is cosine theta from the given, right? While x is sine theta, again from the given. Okay, so plug in y is cosine theta, x is sine theta, and then simplifying will result to cosine squared theta minus sine squared theta. All right, and if you can still recall, this is an identity, right? This is equivalent to cosine to theta, or the double angle identity of cosine. Okay, so this is now our final answer. All right. Now, we actually have another way, an easier way, if you will, to solve this problem. Okay, since we are asked to find the derivative, the total derivative of z with respect to theta, and in terms of theta, we can actually just plug in x equals sine theta here and y equals cosine theta here to get z equals a function of theta. Okay, and then immediately differentiate with respect to theta. All right, so you'll get a derivative, a total derivative that is with respect to theta and in terms of theta. So this one, if we directly substitute the equivalent expressions for x and y, we have here sine theta, cosine theta. Okay, and then take the derivative of z with respect to theta, you'll get cosine to theta. All right. Next problem. If u is equal to x ln y, where x is t and y is t cubed, then find the total derivative of u with respect to t and in terms of t. So again, let's try to solve this one using the method involving partial derivatives. Okay. So again, given, and then for this one, our working equation becomes du dt equals uh, this expression here on the right side. Okay. So we need partial derivative of u with respect to x. We need the derivative of x with respect to t. We also need partial derivative u with respect to y, and lastly the derivative of y with respect to t. Okay, so let's first determine the partial derivative of u with respect to x. Looking at this equation, okay, take the partial derivative of u with respect to x. We'll hold y as constant, therefore ln y is constant. So the derivative of x with respect to x is equal to 1. So 1 times ln y, therefore this is ln y. Okay, then let's find the partial derivative of u with respect to y. Next, again looking at this equation, hold x as constant. So the derivative of ln of y with respect to y, this is 1 over y. Okay, so we have x over y for the partial derivative of u with respect to y. And then dx dt, let's look at this equation. Take the derivative of x with respect to t is equal to 1. And then lastly, dy dt, and let's look at this equation. Derivative of y with respect to t, that's 3t squared. All right, so let's plug in these equivalent expressions to the working equation. So we have ln y, this is the partial derivative of u with respect to x, right? Ln y. Then dx dt, this is the derivative of x with respect to t. Partial derivative of u with respect to y, x over y, and then dy dt, that's 3t squared. Okay, and since we are asked to express the total derivative of u with respect to t in terms of t, then we have to convert y and x into their equivalent expressions in terms of t. Okay, so y from the given is t cubed, so we now have here ln of t cubed, and then x is t. Again, y is t cubed, so just plug in the equivalent expressions and then simplify. Okay, so for the first term, we have here a logarithmic function. We can apply the power property, right? Bring down uh, the exponent of the argument, in this case 3. So 3 here becomes the coefficient of the logarithmic function. So we have here 3 ln t, then uh, t times t squared, that's t cubed, divided by t cubed. So it will cancel out. Therefore, we now have, or we only have 3 for the second term. So overall, this is the total derivative of u with respect to t and in terms of t. All right. You can try to uh, solve for the total derivative of u with respect to t in terms of t by directly substituting the values or the equivalent expressions for x and y to the equation for u, right? So in this case, u is x, where x is t, so just plug in, right? And then ln of y, where y is t cubed, so ln of t cubed. Again, apply power property, so we now have 3 ln or 3t ln of t. Okay, so this is actually an easier way to find the total derivative of u with respect to t, because our equation now is directly in terms of t. Okay, so you try this one and see if you can get the same derivative. All right.